We were discussing about the functions of random variable, and we will continue our discussion on this. Okay. So we know that if we have a function, we have a random variable x which is having a distribution which is fx of x, then we define a random variable, another random variable y, which is a function of x, that means g of x. Then what is the distribution of y? Then what is the PDF? Then PDF of y, which is nothing but fx of fy of y. Fy of y is the question. Okay, this is what we have to find out. Okay, fy of y. So to find this in a easiest way, we have a fundamental theorem. So the fundamental theorem the fundamental theorem, which says that if you know fx of x, then you can find fy of y by using the following formula. It is nothing but fx of x1 divided by g dash of x1, which is the absolute value of g dash of x1, plus f x of x2 divided by the modulus of g dash of x2, and so on till fx of xn divided by g dash of xn. Okay, so and so on. This is the fundamental formula. Now what is this x1, x2, etc.? x1, x2, xn, etc. are nothing but the root of the function g of x, and g modulus of g dash of x I is nothing but the absolute value of the derivative of, that means the first order derivative. Okay, the first order derivative of g of x. Okay, so this is the fundamental formula. This fundamental formula you have to remember to find the derivative of g of to find the probability density function of the random variable. So we will see an example. Suppose you have a function y equal to x square, then you have two roots actually for this, and you know this x is a random variable with fx of x is given to you. Then what is the, then you have to find fy of y. This is the question, you have to find fy of y. So how to find this? So we will see how to find this, how to solve this, how to find fy of y. So you know that y is a random variable, which is y is equal to x square. Then if x takes the value small x, then y takes the value small y. Okay, that you know this thing. And this x can be many things, x1, x2 or x3, many can be any value, but all this will give you some y, the random variable, all this will give you the y. Okay, so it is a many to one function anyway. So in general, so what we are going to say is that you have the roots for this function. If y is equal to x square, then you have x will take the two values plus or minus square root of y. That means you have two roots. x1 is nothing but plus square root of small y, and x2 is nothing but minus square root of small y. So these are the two choices. So these are the roots now. Okay, as I have told in the previous slide. So these are all the roots actually. So this roots of g of x. So the roots of g of x for this particular problems are plus square root of y and minus square root of y. Okay, and now we will find the g dash of x1, and you know that g of x is nothing but x square. So g dash of x is nothing but 2 into x. Okay, in general. So g dash of x1 is nothing but 2 into x1. What is x1? x1 is nothing but square root of y, and g dash of x2 is nothing but 2 multiplied with the minus square root of y. Okay. Now we will find the absolute value. The absolute value of g dash of x1 is nothing but 2 into square root of y, and the absolute value of g dash of, so it is nothing but the absolute value of 2 into square root of y is nothing but 2 into square root of y, and g dash of x2 is nothing but the absolute value of minus 2 into square root of y. So this is again 2 into square root of y. Okay, so we have seen we have omitted the negative sign. That's what we are taking, okay, when considering the absolute value. Now we will talk about the fy of y, which is nothing but fx of x1 divided by g dash of x1, we'll take the absolute value, plus fx of x2 divided by the absolute value of g dash of x2. Okay, so this is nothing but fx of x1, you know this is fx of x1. What is x1? x1 is nothing but the square root of y divided by g dash of absolute value of g dash of x1 is 2 into square root of y, plus fx of x2 is nothing but minus square root of y divided by 2 into square root of y again. Okay, so this is what the PDF. So it's very simple to obtain the PDF. So you see here, this is nothing but the PDF of y. So we have seen the same thing before. I will show you. We have already seen this. Okay, so we are getting the same answer like that. Okay, now so we will see the proof of this particular theorem. Suppose you have a g of x which is shown like this. You have a g of x something like this. Okay, and you have your PDF something like this, your PDF something like this. Okay, now this is your PDF fx of x, and this is x, and this is x. Okay, now suppose you are talking about the roots of this function, so you can see here g of x is having the roots here. This is the root, okay, and this is also the root. Okay, now let us consider, let's say this is x1 and this is x2 and this is x3. Okay, now it is giving you some y. You can see here it is giving you some y. Okay, so the y is coming from, actually from x1 is also giving you y. Similarly, your x2 is also giving you y, and similarly the x3 is also giving you y, right? So your y is coming from basically from three things, actually x1, x2 and x3. Okay, so y is giving you the y is coming from three values, and you know that fy of y, if you multiply with dy, then I told you it is nothing but the probability that the random variable y takes the value between the small y and y plus dy. Okay, this we have already seen. It is nothing but the delta area, that is a small area, okay, under fy of y. But you know that y is coming from three things, so it is nothing but the probability that your random variable x takes the value between x1 and x1 plus dx1. Okay, because you see, if you take a small area here, this is a small area you are taking. Okay, this area, if you take, sorry, this is the small area, that means you are considering here dx. Okay, similarly you can consider here also the small area, so this area, so this is giving you actually this is dx1 and this is dx2. Okay, and similarly you have something like here, and this is giving you dx3, And you can see here, if all of this are giving dx1, dx2 and dx3, it is giving you another a small delta change in the y. That means it is giving you a dy. So your dy is coming from, I can say that your dy is coming from dx1, then it is coming from dx2 and dx3, right? It is coming from dx3. So three things. So that's why we will talk about our probability of y it is coming from. That means fy of y into dy is coming from the probability that it is nothing but the probability that y takes the value between y and y plus dy. It is coming from x1 and x1 plus dx plus the probability that x takes the value between x2 plus dx2 and x2 plus the probability that x takes the value between x3 and x3 plus dx3. Okay, so this is nothing but, you know, by using this basic definition, that we know this is a note, I will write it. Fx of x is nothing into dx is nothing but the probability that x takes the value between x plus dx and x. This we have already seen in the previous lecture, so we will use this idea. So it is nothing but fy of y into dy is nothing but fx of x1 into dx1 plus fx of x2 into dx2 plus fx of x3 into dx3. Okay, so you have fy of y into dy is equal to fx of x1 into dx1 plus fx of x2 into dx2 plus fx of x3 into dx3. But you know that your dy by dx, we have dy by dx is nothing but your g dash of x. So dy by dx1 is nothing but g dash of x1. Okay, so we will have the proof like this. So we have something like now we have fy of y into dy. Sorry, I will remove this dy from here. Okay, and I will write only fy of y. This is nothing but fx of x1, okay, into dx1 divided by dy plus fx of x2 into dx2 divided by dy plus fx of x3 into dx3 by dy. So this is nothing but fy of y, which is fx of x1 divided by dy by dx1 plus fx of x2 divided by dy by dx2 plus fx of x3 divided by dy by dx3, right? But you know that we will try to avoid the problem that the PDF takes the value negative, so we'll take the absolute value here. Okay, otherwise if you have a PDF which is y is equal to minus x, for example, if you have a question like this, y equal to minus x as the function, then your PDF sometimes will take the negative value because the derivative is minus 1, and you know that by using the axioms of probability theory, the PDF will never take the negative value. So we will take the absolute value to avoid the negative values for PDF. Okay, so we have fy of y is nothing but fx of x1 divided by, you know, this is nothing but absolute value of g dash of x1, because that's what we have seen in the previous slide, okay, not previous slide, in this slide itself I have already explained. So in general I can say it is dy by dxi is nothing but g dash of xi. So this is nothing but plus fx of x2 divided by absolute value of g dash of x2. So this is how we can prove this x3 divided by g absolute value of g dash of x3. So this is nothing but the proof of this. Okay, for this particular example only while proving I have considered only 3 roots. That's why we have 3 roots. If you have lot of roots, so then it will be like plus fx of x4 by g dash of x4 and so on. Okay, so this is nothing but the proof of this. So we will see another problem. We have an example now. We have the PDF of a random variable x as 2x, where x takes the value between 0 and 1, and it is 0 elsewhere. This is the PDF of the random variable x, and we want to find the PDF of y, which is nothing but 8 times x cube. Okay, 8 times x cube. Okay, now we are going to solve this. We have y equal to 8 times x cube. We have it is a strictly monotonic function, it means strictly increasing function. Okay, in 0 and 1, because 2x is something like this. Okay, it's 0 and 1. It's a monotonic function between 0 and 1. Now we want to find the PDF of y is equal to x cube. Now we will see what is our g dash of x. This is y is equal to x cube. So g of x is nothing but 8 into x cube. So what is g dash of x? G dash of x is nothing but 8 into 3x square, which is nothing but 24x square. Okay, it's 24x square. Now what are all the roots of this polynomial? You see here x is taking only the positive value. So y is equal to 8 into x cube will take only the positive values, because x is always positive. Okay, so y is equal to x square, so y is equal to 8x cube will also take the positive values. Okay, now we have something like g of x is equal to 8 into x cube. So now we will see what is the root of this equation. Okay, what are all the roots of this equation? Okay, so what are all the roots of this equation? Since we have y equal to 8 into x cube, we have y equal to 8 into x cube. Okay, so y by 8 is nothing but x cube, which implies x is equal to cube root of y by 8. Okay, it is nothing but cube root of y by 8. Okay, so it is nothing but 1 by 2 into cube root of y. Okay, or I can say it is equal to 1 by 2 into y power 1 by 3. Okay, so this is my x. Okay, so I have this, it is nothing but 24 into x square. So I can write, I can find the g dash of x. So g dash of x is nothing but 24 into x square, which is nothing but 1 by 2 into 24 into x is nothing but okay. So 24 y is equal to 24 into x square, and so it is nothing but 24 into What is x? X is nothing but 1 by 2 into y power 1 by 3 the whole square. So this is nothing but 24 into 1 by 4 into y power 2 by 3. Okay, y power 2 by 3. So this is equal to 24 by 4 is nothing but 6 into y power 2 by 3. So we got our g dash of x. Okay, so because here only one root is there, the negative root is not considered because our random variable x takes the value from it takes the value only between 0 and 1. It is always positive. So now we will have our PDF as follows. We have the PDF fy of y is nothing but fx of x divided by g dash of x. So fx of x is nothing but it is 2x 2 into x divided by g dash of x. We have already seen g dash of x is 6 into y power 2 by 3. 6 into y power 2 by 3. We will take the absolute value, but you know that there is an x here. What is this x? We will see. You know that we have x as the formula that we have already derived. Okay, we have already derived actually x takes the value, sorry, x is equal to 1 by 2 into y power something like y power 1 by 3. So our fy of y is nothing but 2 into 1 by 2 into y power 1 by 3 divided by 1 by 2, sorry, divided by this thing, that means 6 into y power 2 by 3. Okay, so you see here this 2 and 2 will cancel. So this is nothing but 1 by 6 into y power 1 by 3 divided by y power 2 by 3. Okay, so this is equal to 1 by 6 into y power minus 1 by 3. Okay, but what is the range of y? Y takes the value from between some limit. What are these limit? For example, a and b. What are this a and b? You know that y is equal to 8 into x cube. When x is equal to 0, when x is equal to 0, then your y will take the value 0. When x is equal to 1, your y will take the value 8. Then your y will take the value 8 into 1, which is 1 cube, which is 8. So your y will be having a value between the range 0 and 8. So this is very important. So this is your fy of y. Okay, so this is the distribution of fy of y. So this is very easy to find out if you know how to take the differential of a function. Okay, next we have another problem. If you have a random variable, x with the mu x and sigma square as the variance, and your x is given as normal distribution, x is given as normal distribution, then these are all given. Okay, then you have to find y equal to e power x. Okay, you have to find, then you have a function which is y which is equal to, then for y equal to e power x, what is the PDF of y? That means you have to find fy of y if you are transforming like this. Okay, you know that our g of x is taking the form e power x, right? This is our g of x, and our x is a normal distribution. It will be usually represented like this. It's normal distribution with the mean mu x and sigma x square. This is the usual representation for the normal distribution. Okay, this you can see in many research article. So this is g of x and this is your y. Okay, then you know that e power x is equal to y, then x is equal to ln, that means natural logarithm of y. Okay, x is equal to natural logarithm of y. Okay, so this is the root actually, and your y is equal to e power x is the function. Okay, now you will find the g dash of x. G dash of x is again, it is nothing but e power x. Okay, since you have g dash of x is nothing but d by dx of e power x, so it is again e power x. Okay, e power x. And what is that e power x? E power x is nothing but y. Okay, now you have the basic idea that e power x is strictly a monotonic function. This e power x is again strictly a monotonic function. This is e power x. It is strictly a monotonic function of x. Okay, so you don't need to worry about it because there won't be two values. There will not be any two roots for this. Okay, and you know that we will be considering. So you have got this idea. Now we will find fy of y. Fy of y is nothing but fx of x divided by g dash of x. So it is nothing but fx of x divided by g dash of x is nothing but the absolute value of g dash of x is nothing but the absolute value of y. Okay, so the absolute value of y means the y is always greater than 0. Okay, that means you are always considering the positive value, so it is nothing but the y. Okay, this is nothing but, you know that fx of x is a normal distribution, so you should know what is a normal distribution. It is nothing but 1 by square root of 2 pi into sigma x square into e power minus of x minus mu x the whole square by 2 sigma square. Okay, so we will find fx of x here now. So 1 by, we will see fx of x, so it is 1 by square root of 2 pi into sigma x square, and we have a y. This y we will put it here. Okay, we will put it here, y. Okay, next we have e power minus of, what is our x? You know that x is nothing but the logarithm of y. Okay, so it is nothing but ln of y. Okay, minus mu x the whole square divided by 2 sigma x square. Okay, so and also given that our y is always greater than 0. Okay, so this is the PDF for our y. Okay, so this is how to find the PDF. So this is very simple, just use the formula. This is the formula. Okay, and you just need to take the differential. We will see one more example. If the distribution for the same problem, if the distribution is log normal distribution, sorry, not, this is known as log normal distribution, log normal distribution. Okay, this is known as log normal distribution. I think this is enough for you, I think so. Okay, so this is how to solve the problems which are related to the functions of the random variable. So anyway, I would think it is good to have one more problem. Let us assume that you have a random variable. Another example, you have a random variable x which is having fx of x, which is nothing but alpha into e power minus alpha x. It is nothing but the exponential distribution. Okay, exponential distribution. This is a PDF of this. Okay, PDF is showing an exponential characteristics. That's why it's an exponential distribution. Then you have a function y is equal to logarithm of x. You have to find the PDF of y. Okay, this is the question. But you know that your fx of x is nothing but alpha into e power minus x, and your g of x is the function which is nothing but logarithm of x. Okay, this is nothing but your y. So logarithm means you can natural logarithm. Okay, this is natural logarithm. It's not simple. It's a natural logarithm. Okay, natural logarithm ln of x. So what will be x? X is nothing but e power y, right? Directly you just take the exponential, then you will get x is equal to e power y. That is this is e power y. Okay, and you know that our y is you know that y is equal to ln of x. So your x is nothing but e power okay, that's enough. Now we will see, you can see here, this is again a monotonic function. So we will see the fy of y is nothing but fx of x divided by g dash of x, and we have to find the g dash of x. Now what is g dash of x? G dash of x is nothing but d by dx of ln of x. So it is nothing but 1 by x, 1 by x. And what is this 1 by x? X is nothing but e power y. Okay, because x is e power y, this is coming from this direct relationship. So this is nothing but fx of x divided by the modulus of g dash of x, means the modulus of 1 by e power y. So this is nothing but e power y. Okay, the modulus of e power y into fx of x. So this is and you know that x is equal to e power y. So this is equal to e power y into fx of x is e power alpha into e power minus alpha x. But you know, again, by using the same equation, that means your x is nothing but e power y. So this is nothing but e power y into alpha into e power minus alpha into e power y. Okay, so this is the characteristics. Now we will see what is the range of this value of x. Okay, and you know that y is equal to ln of x. This is our function. Our function was y equal to ln of x. So if x is equal to if x is positive, you see here your y can take the values, whether it will be positive and negative. Yes, it will take the negative values also, since x is changing from minus infinity to infinity. You can see here your y also will take the values between the minus infinity to infinity. So y will take the values from minus infinity to infinity. So this is how to solve this problem. So this is the answer. Okay, this is the answer. I hope this is clear to you. So next we will discuss about very important concepts regarding the two-dimensional random variable. So this part is over. So we will discuss about the new topic, which is nothing but two-dimensional the random variable. Okay, random variable. So here actually we have the previously we studied about one-dimensional random variable. So but here we are going to define about the two-dimensional random variable. So before that I will refresh the idea of one-dimensional random variable. That means you know that the probable cumulative distribution function fx of x is nothing but the probability that x takes the value. Fx of x is nothing but the probability that x takes the value from minus infinity, the probability that x takes the value less than or equal to x. Okay, similarly fx capital small fx of x is nothing but the d by dx of fx of x. Okay, similarly this is for the continuous random variable, and for the discrete random variable, we have the probability mass function, which is represented as px of xk, which is nothing but the probability mass function. Okay, this is nothing but the probability mass function. I hope this is clear to you. And the first equation, actually this is fx of x is probability that x less than or equal to x is the cumulative distribution function both for the continuous random variable and discrete random variable. The definition is same anyway, and the notation will be different for PDF. Actually this is showing the PDF and this is the probability mass function, okay, PMF, that we have already seen. Now we are talking about 2D random variable, so we are talking only about a random variable x here, but here now we are talking about two-dimensional random variable. That means we will talk about a pair which is x and y. Then we can define our cumulative distribution function. The cumulative distribution function can be defined as fxy of xy is nothing but the probability that x takes the value less than or equal to x and y takes the value less than or equal to y. It's very easy. That is, you are just extending into 2D variables, two-dimensional random variables. This can be extended for three-dimensional random variables also. Similarly, fx of x will be replaced with, we have fxy of xy is nothing but we will take the two derivatives d by dx. That means we will first differentiate with respect to partial differentiation dou by dou x and dou by dou y of fxy of x comma y. Okay, this is nothing but the PDF of the random variable. Okay, similarly we have the PMF function for the, this is all for the continuous random variable, and this is for the continuous random variable and for the discrete random variable. But for the PMF, so this is PDF, the first one is PDF. Now for the PMF, it is nothing but pxy of xk and yk. This is the representation. Okay, so it's very easy thing, it's not a difficult thing. Okay, now we will see certain important characteristics. Sorry, I have forgotten to write this dou square because it is a second differential, because we are differentiating with respect to x and differentiating with respect to y. Now we will see, now we have another thing for 1D random variable. For 1D random variable, we have fx of x into dx is nothing but the probability that x takes the value between x and x plus dx. Okay, that means area under the fx. This is a small area, delta area. Okay, small area. But for 2D random variable, so this 1D and 2D random variable x and y, we have the same thing, fxy of x comma y. We will talk about dx and dy. That means it is a small volume, this is a delta volume. Okay, it's nothing but the probability that x takes the value between x plus dx and x, okay, comma, it takes the value, y takes the value between y plus dy and y. Okay, so just the extension. Okay, now we will see a very important concept, how we can talk about the what are the properties of the CDF, properties of CDF. That means fxy of x comma y. So the first property says that fxy of minus infinity and y is equal to 0. I told you whenever we are talking about minus infinity, it will be always 0. Okay, similarly this will be same as fxy of x and minus infinity for y, so this will be 0. and we have, if we talk about all infinity, that means x and y as infinity, I told you we have always 1, because we know fx of infinity for 1D random variable, for 1D case fx of infinity is 1. Similarly, if both are infinity here, it will be 1. So I'm not going to include it here anyway. So this is the first property. Then the second property is nothing but the probability that x takes the value between a and b, given that y is less than or equal to y, is nothing but, not given that, at the same situation the probability that x is between a and b and y is less than or equal to y, it is nothing but f of b, fx y of b, y I will put it like this, minus fxy of a, I will put y like this. Okay, same thing. So it is same like the previous formula, because you know that the probability that x takes the value between a and b is nothing but fx of b minus fx of a. But here there is a y also, that's why we are including y also. So that is okay. Now then we have another formula. This is same like the second one. The probability that x takes the value less than or equal to x, given that y takes the value between a and b, is nothing but fxy of x, and this is b, minus fxy of x and a. Okay, that's it. So it's same like the previous formula. Next is the fourth formula, is nothing but the probability that x takes the value between a and b and y takes the value between c and d, is nothing but fxy of, this is b and this is d, minus fxy of b, sorry not b, fxy of a and c. Okay, okay, but that is not enough. That is not enough. Okay, this is between c and d, that is not enough. Okay, so it will be, you have to take the other combination also, minus fxy of b comma c plus fxy of a comma c. So this is the formula. So this is slightly different anyway. Okay, it can be proved. Now we have seen all the properties. Now we will talk about the marginal densities of K. Marginal density. That means if you have the PDF, you have the PDF for the 2D random variable, PDF for 2D random variable xy, the pair xy as fxy of xy. Suppose if you want to find the marginal PDF, that means if you want to find the density of x, okay, that means you are averaging throughout all the possible values of y, then fx of x is the marginal PDF. That means actually you have a two-dimensional random variable. Now we are talking only about the x, given that y takes all the values. That means you are assigning the certainty for the y. That means you are to integrate from minus infinity to infinity. You have the PDF fxy of xy, and you have to integrate with respect to y. That means you are averaging throughout all possible values of y. That is known as fx of x. Similarly, you will be getting fy of y is nothing but integral minus infinity to infinity fxy of xy. You want, if you integrate for all values of x, then you will be getting the PDF only with respect to y. Similarly, so these are all the this is known as the marginal PDF. Okay, marginal PDF. This is the marginal PDF of x, and this is the marginal PDF of y. Okay, so This can be this formula is same for the, this is for the continuous random variable, as I told you, continuous random variable. Similarly, for the discrete random variable, you can have the same thing for the discrete random variable. So for the discrete random variable, you have, instead of integration, you have summation. If you have pxy of xi and yi, okay, if you are integrating, means you are summing for all values of suppose this is j, okay, j. So you are integrating for all values. For example, this is, sorry, this I have made a mistake here. This is I and j, okay, this is I and j. I will I and j. So what we are going to do is that for discrete random variable, we are adding for all values of j. That means we are integrating with respect to y, then we will be getting px of xi. Okay, so this is for the discrete random variable case. Similarly, the marginal PDF for the discrete random variable, in this, the analog for this, okay, the analog for the second one is nothing but we want to find py of yj, then we have to integrate. That means we have to add it for all values of xi, this is yj. Okay, if you are adding for all values of I, that means you are averaging for all values of x, then you will be getting py of yj. So this is the case for the discrete random variable. Okay, so these are all the marginal PDF. Both are marginal PDF. So one for the continuous random variable and another for the discrete random variable. So this is for the continuous random variable and the other one is for the discrete random variable. I hope this is very clear to you.